Okay, here we go. I've been talked into posting this video by a couple of friends on the forum. I've been over and over this machine for the last 4 days, and now I just want to see if anyone else can make any sense of it. First thing I need to show you, and that will become apparent in the test, is of course we have our variable power supply here. And what I've done is I've hooked this up the same way as the input is on the machine that we're going to look at. Excuse me. 100 ohm resistor, one of the light globes we're doing, and then back out to the negative side of the power supply. The positive is coming out, going through our amp meter, and then of course back into the start of the system. Which is this bit here. This is our positive and our negative input. So what I want to show you is that 40 milliamps at 4.72 volts. That is how bright the globe is. So just like I said, keep a note on this because it will become important later on in the video. So it's 40 milliamps at 4.72 volts, and that is the globe right there. Now the other thing I want to show you is the output side is like this on the machine, and I will wind the power supply down a bit, get it to 80 milliamps. Pretty close, 79.9 at 3.3 volts, and that is the brightness of the globe. So the other thing you're going to need to know is how the input of my system is hooked up. We have our battery, which in this case is going to be 26 volts. I'm using two 12s hooked in series. They are fully charged to about 26 volts. We're coming out of the positive. We're going through the globe and the 100 ohm resistor as we have this set up here, and as you can see it is the same here. Out of that resistor we are going to a cap, which is this one, and then out of that cap we are going back down to the negative side of the battery. The load the machine is drawing is pulled off of this cap, so that's just something to keep in mind as well as to how exactly the machine is hooked up. So what I'll do next is I'll get set up, hook all the meters up to the machine, get the scope ready, and we'll go over it. I'll show you what I have, and then we can take it from there. Okay, there was one other thing I forgot to show you. Hooked up as we showed before, drawing out 40 milliamps, and that was the voltage across the globe itself. As you can see, it's 0.832 of a volt at 40 milliamps. So I just forgot to show you that, so I'm very tired, so we've got to put that in as well, because that will also come apparent a little later on. Okay, back to setting up. Okay, first what I'm going to do is go through and flatten all the caps. And of course this one won't have any in it because it's got the light globe hooked up to it. Okay, so this meter here is our amp draw from our 24 volt battery bank, or what is supposed to be 24 volts, 26. This battery here, this meter here is that cap I just sparked out. which is our feed cap to the system. It's getting a little bit of recovery voltage back in it, but that's 0.4 of a volt. This is our battery voltage here. This meter here will be showing you the amps going through the globe. The power for this globe is being drawn off of this cap and this cap. I have bare steel wire here just so I can hook the scope up across it. Coming out of the positive, going through the meter, back through the meter, back out of the meter, sorry, through the globe, back into the negative side. Now the rotor is one I was trying out. North-south, north-south, alternating magnets. And I believe this is where what looks like to be extra power is coming from, is the generating effect. If I spin this, you watch, this of course is our drive cap. You can see it generates a voltage in that drive cap when I give it a spin. It also, from the trigger coil, is generating an extra voltage going into our it actually goes into this cap, which is fed back into the cap that's collecting the back EMF, which also goes into the globe, and that's from the trigger side, and that's a little bit different than the standard Bedini circuit as well. Also the way that I hook these 4 caps up, I'm not going to go into my circuit too much, I just want to show you what effect I have and let you all ponder on it and see if anyone can tell me what looks like to be really is what it is. So I'm going to take the meter, which is our amp meter set on the 200 milliamp scale, hook it on here. You'll see this light glow until this cap here reaches the voltage of the batteries. I'll try and get the meter in there at the same time. As you can see, starts filling the cap up. Our amp draw goes down until it gets to nothing. This is because this cap is filling up, as you would have seen in the drawing how I had it hooked up, and the potential difference between the cap and the battery is becoming closer and closer. It's 26.1 on the battery, 26.17, 18 now on the cap, which if this had another decimal point would be what it is. So now the potential difference is 0, no current can flow, thus our light has gone out, and we are down to 0.1 of a milliamp current draw, which will also disappear, but that is nothing at all. 100, oh there you go, she's gone. Right, the cap is now full to the exact voltage of the batteries. I have this set in the best spot, which I've marked for the power conversion. So we will start it up. We're going to measure the voltage across this globe, and we will also have this meter hooked up to show us here the potential difference between the cap and this battery. Of course, at the end we'll take this globe out and put it in here and put this globe in here, so you can see there's no hanky-panky. I will take this one out first and you will see that the current will stop flowing and the machine will stop, so we know it's drawing from the batteries. So we will let it build up speed. This time I'm not going to be doing the whiteboard thing, calculating volts and amps and all that. use are welcome to do that while we're going through the video, but this one is just purely to show you what seems to be going in and what seems to be coming out. Now keep in mind, we've all seen the effect happen with a DC pulse. This is pure DC out and pure DC in, and you will see that on the scope. And I have the scope set at 0.2 milliseconds, and the times divide, and 2 volts and the volts divide, and I think you'll agree that's a very, very deep look into our line. As we can see, we are indeed zeroed out, almost. Yep. Okay, there's it right there. Back onto DC. Alright, she's pretty much well up to speed. Our running voltage is 26 volts exactly. The run cap is on 21.6867 volts. So that is our potential difference in the system. Now, what we would normally do is go by our amp input, by our battery voltage to give us our input current, but in this case, the way that it's hooked up, our input voltage, our potential difference is 25 or 26 minus our 21.64, and it is that potential difference that we must times by the 37.4 milliamps to get our input current. And I can assure you that this little 6-volt globe having 24 volts going through it, even with the 100 ohm resistor, goes very, very bright, if not pops. And using this, I will show you that at the end of the video. Okay, so at the moment we've got 80 milliamps going into this globe, and as you can see, this globe here, which is our input globe, is only barely lit. Now that is where the first part of this video comes into it. So what we'll do now, we've got our meter, and I'm going to show you the voltage across that globe, and I should hook it up the right way around. Okay, we've got our positive side on the input side and the negatives hooked before the resistor onto the other side of the globe, and there is the voltage across that globe. Is 0.781 of a volt, and like I said, that's where the first bit of this video comes in, where I showed you this system hooked up to our power supply. We're now going to measure the voltage across the other globe, which is our output globe. Let's grab the meter. Negative onto negative, and of course our positive onto positive. Like I said, these two wires are coming from the cap, going through our meter and then through our globe. It is 3.71 volts at 80 milliamps. Once again, the little test at the start of the video across the globe will show you that's very much the same. Okay, so now we're going to have a look to make sure it is pure DC across our globe on the output. And as you can see right there, that is saying to about 3.6 3.8 volts. And the line is dead flat, even at that resolution. There is not a little ripple in it. Pure DC voltage. The meter confirms it's 3.72 volts. So we have the meter and the scope saying that is the correct voltage across this globe. The globe lit up like that is also saying that is the correct voltage across the globe. We will now put the scope across the input globe. Test it here. Okay, as you can see, we're on each side of the globe. We'll hit 0 on this. You can see it is set correct. And you can see that is saying about just under 1 volt. Very close to 1 volt. Now tail crank meter back off. And I'll put the meter across the globe also, if I can get it on there. Okay, our meter is saying very close to 0.8 of a volt. Like I said, that is right on the second line, so that is in fact 0.8 of a volt. Once again, our meter and our scope are showing the same voltage, and as you can see, that is a pure DC line. Once again, zero it out. Not a ripple in it. So that's pretty much, unplugged the wrong one. All I can show you with the scope and the meters of the voltage across the input globe and the voltage across the output globe. As you'll see, it is pure DC. Right, the other thing we were going to do is pull the globe out so you can see there's no hanky-panky. Now the machine will keep running because it's generating its own power, but it will eventually start to slow down as it is doing now. Yes, I still have the globe. Okay, we will swap the globes. We'll disconnect the meter so we don't blow the transistor up, because that was the globe, wasn't it? I will have to swap them again because I don't know if that was the globe or not. Okay. We'll hook the meter back up. Once again, the globe will glow till the cap fills up. Our current will go down as the cap is filling up, and this thing will start up by itself. It is of course screwed to the bench so it doesn't move when I spin the rotor. I will actually unscrew that because I've seen what people say, the gurus, when they come in. There's always a hidden power source somewhere. Okay, nothing hiding behind door number 1. As you can see, it's just a blank bit of wood, no holes anywhere. You can even move it back a bit if you want. Other than the fact that I just pulled the lead off for the power supply. Once again, get that a bit closer, take the globe out. No more current draw from the batteries. Put that one there this time so I don't get mixed up. I'll stop that. Put this globe in. You'll see it go up until it's finished pumping up the cap. Take this globe, which now has a little bent wire, and put it back in this hole. Okay. So that's what I have, guys. Unless there is some way that you can pass more straight DC current through the input globe and not have it light, then you're putting into the output globe. I really don't know. I'm not making any claims here, so for all you gurus out there and physicists that always seem to pop up on this sort of thing, please remember I'm not making any claims. I'm interested in everyone's comments on it, but it is what it is. And I just do not see any possible way of putting in more current through the same type of globe and not have it glow when that current is DC, smooth DC. Oh, there was one other thing we were going to have a look at. I will in fact do that now. Get rid of this mess. That's in there tight. There we go. Yes, I'm going to use the same globe, just so there can be no question. I'm just going to show you what happens when we put 24 volts through that globe with just a 100 ohm resistor. If I can find another lead. There we go. This is what the system should have been reading if the meter was correct. Oh, there we go. That's how bright the globe should have been. So that is what we have here. Actually, what we will do is just see. I'll put our amp meter on there, which I haven't done before, just to see how many milliamps that does pull like that. There you go. So it definitely wasn't the 24 volts going through this globe, it was definitely only the potential difference between the cap and the batteries. Alright, Well, that's about it. That's as best I can do. That's as clear as I can show it. I don't know what else to do, so if anyone's got any ideas as to how you can pass more current through a globe, DC current, and not get it to light, and yet less through another one and get it to light, pure DC current, I'm open to suggestions. That's it from me. Cheers from the Tin Man. Just before you thought it was safe to go and get a coffee, there was something else I wanted to show you as to why I believe the system is drawing very little current. So what I will explain again is 2 caps are used to store the power for this globe. The other 2 caps are storing the power to run the motor. But it's also configured a very similar setup to my single battery SSG that I made about a year ago, in which that it both runs and charges the run caps as well, and this takes effect when I disconnect the run battery. So what I'm going to do is stop the rotor so the system stops, and I'll show you just how long it takes this globe to pull down these caps. Now they do look physically big, but as you would know, they're only 10,000 microfarads each, so there's only a 40,000 microfarad capacity in the whole system. And when you put an incandescent bulb on a cap that size, it will indeed pull it down fast, which I will show you right now by stopping the rotor. This will show you how long it takes for that globe to pull down the 2 caps that are storing the energy to run that globe. Now that's 20,000 microfarads that just killed, and like I said, the whole system is only 40, so maybe twice as long it would glow for to pull down the complete 40. Now what I'm going to do is start the system back up. Once it's up and running to its running speed, I'll disconnect the battery, our run battery, and I will show you how long not only does it supply enough power to run itself, but also how long it will run that globe for. So I have the batteries going through our ammeter again, of course. When I disconnect that, you'll see that go to 0, which means we'll be putting nothing into the system. And this will just give you an idea. It's not going to run for hours, but it will run for a short time. And keeping in mind it's still going to be keeping this globe going as well as running itself. It is starting to rain. I do have a tin roof, so it may get a little noisy. Okay, we're nearly up to running speed. I reckon that'll do us, give you an idea anyway. So I'm now going to disconnect the power input to it. So it runs for about 5 seconds and then it starts to slow down. So that is not only running the motor, but as you would have seen, it was keeping that globe lit fairly bright as well. So it's just something else I wanted to chuck in there, show you how efficient the system really is, and just another way to back up that what I think is going into the system is actually what's going into the system. Okay, well I'll let you go this time and have your coffee. So cheers from the Tin Man.